Hi, all, and welcome to our second lesson of our supplemental chapter. This is an extension of section 5.2 that we did way back in February. And in 5.2, we learned about Riemann sums and the fact that you could take a bunch of rectangles and add them together to get the area under a curve. And we looked at that using sigma notation. So the difference for today is instead of using rectangles, we're going to be using trapezoids. So if we try and find the area under a curve using trapezoids, we get a bit better of an estimation than if we use the same number of rectangles. So for example, if we use our Riemann sum with, say, 4 rectangles, we will get a less accurate picture of the area compared to if we use 4 trapezoids. So in order to add up the areas of all the trapezoids, we first need to know how to find the area of one trapezoid. So I've got a little trapezoid over here on the side, and the area of a trapezoid is m plus n over 2 times h. Now notice that our trapezoids will not usually be in this orientation. Our trapezoids are usually going to be almost like sideways like this, where h is actually going to be like the width of our trapezoid if we think about it from side to side in our picture, and m would be one of the heights, and n would be the other height. So what that means for us is when we add up a bunch of trapezoids under a curve, h is going to actually be the width of those trapezoids, which will translate to be our delta x. And m and n will be two different y values on that curve. So it's almost like you're taking a left and a right endpoint at the same time. So if we were looking at a curve, say below, and we wanted to go from some point A up to some point B and find the area under that curve, our delta x is found the same way as it was with rectangles, b minus a over n, where n is the number of trapezoids. So n is the number of subintervals or trapezoids, that same n there. So to find the area of each of these trapezoids, for example, that would mean that our h is now this distance, which is actually delta x. And our height are going to be different f of x values at the corners of these trapezoids. So this would, for example, be n, and this one here might be n. So if I wanted to find the area for this picture, for example, your total area for this diagram is the sum of 4 trapezoids. Okay, so if I have this f of x here, we're being told that we're going from A to B into 3 subintervals. So we're going to have one, oops, that one didn't really line up very well, did it? Let's try again. One trapezoid that's going to go from here to here. We'll call this one x1. We'll call this next one x2, and maybe I'll relabel B as x3, and I'll relabel A as x0. Okay, so we're going to have 3 trapezoids here. And our height of each trapezoid is actually kind of now our width, because we've got this trapezoid turned sideways. So this here would be our h, which is actually our delta x. And this here would be m and n, our two different side lengths of our trapezoid. So the area of the first trapezoid is going to equal m plus n. M here is f of x0, the height at x0. N is the height at x1 over 2 times h. And h here is delta x. Now, we have an actual expression we can use for delta x. Delta x is actually b minus a over n. You can put this in big brackets here if you'd prefer to keep it a little neater. That's fine. And then we're going to have a second trapezoid. This one's going to be f of x1 plus f of x2 over 2 times b minus a over n. Because our m and our n would now be different. Our m would now be lined up with the x1, and our n would now be lined up with the x2 at y values there. And then we're going to also have trap number 3. I'm going to put this over here just because I'm running out of space. This one's going to be f of x2 plus f of x3 over 2 times b minus a over n. So in general, our total area is going to be, if we add all these together, so notice there's a b minus a over n in all of these. So we end up with f of x0 plus f of x1 all over 2 times b minus a over n plus f of x1 plus f of x2 over 2 times b minus a over n. And for this specific example, we had 3 subintervals, so we would only have had one more of these terms, but this is asking us to generalize what our total area would be for n subintervals. So we would keep going until we got to an f of xn. So our very last one would be f of x, whatever n minus 1 is. So for us, that was f of x2 plus f of xn over 2 times b minus a over n. Now what we can do here is we can actually factor out a b minus a over n or a delta x. We could also factor out a 1 over 2 if we wanted to. And we also, if we take a look at this, we end up with 2 of every f of term except for the first and the last term. So f of x1 gets used twice because it's attached to 2 different trapezoids. F of x2 gets used twice because it's attached to 2 trapezoids, all the way up to f of x n minus 1. So f of x0 and f of xn only get used once because they are only part of one trapezoid. So those 2 parts are actually going to not get used twice. So one way we can look at this is let's factor out the 1 over 2 that's in everything, the b minus a over n that's in everything. And what that leaves us with is an f of x0. It leaves us with 2 f of x n's, or f of x 1's, sorry, to f of x 2's, all the way up to 2 f of x n minus 1's, and only 1 f of x n. Okay. In other words, we can write this as 1 over 2 b minus a over n times, we could write this as f of x0 plus f of xn plus the sum from I equals 1 to n minus 1 of 2 f of xi. Now, if we want to, we can continue to expand this, and we could expand our b minus a over n back in and rewrite it. So you'll see a bunch of different options of how you can write this. But usually the most common one is actually this guy right here. So we're going to say the integral from a to b of x dx is equivalent to adding up all of these trapezoids. Okay. We're going to call this the trapezoidal rule. I'm going to rewrite this as b minus a over 2n times f of x0 plus 2x1 plus all the way up to 2 f of xn minus 1 plus f of xn. So usually they will tell you exactly how many subintervals you'll have in the question, or they'll give you your subintervals. And what I mean by that is, for example, let's say we're given this function. We want to find the approximate area under the curve over this interval using 4 subintervals. So this is my n. Okay. So that means that my area, which I know is an integral, which we can find using other methods, but specifically we want to use the trapezoidal rule because in AP they can ask you to use a specific method. This is the same as saying b minus a, which is 2 minus 0, over 2n, n is 4, times, we're going to have f of x0, which is f of 0, plus 2f of x1. Now we need to figure out what x1 is. So we need to know what our delta x is so we can figure out our next x. So delta x is going to be b minus a over 4, which gives us 0.5. So that means our next x is 0.5. And then we have plus 2 times f of 1 plus 2 times f of 1.5 plus f of 2. And this is because my x0 is my a, and my xn is my b. So this is f of x0, and this is f of xn, or because n is 4, f of x4. Okay. And we have an actual function, so we can figure all this out. It's a little tedious, though. So this is 2 over 8, which gives me 1 over 4, times this is going to be e to the 0, plus 2e to the 0.5 squared, plus 2e1 plus 2e to the 1.5 squared. You can square that too if you want, plus e to the 2 squared. You're going to want a calculator to figure all this stuff out in the square brackets. If you plug all that into your calculator, you should get 82.578. So in total, this gives us 20.645 units squared. Okay. I know the question didn't say trapezoidal rule, but on your AP it will tell you if you had to use it. For example, like this one. The values of a continuous function are selected. What is the value of this integral using these specific subintervals and trapezoidal approximation? So the difference here is that your delta x is changing for every single trapezoid that you have. And what that means is that we're going to have to do all of our trapezoids individually. So we need the area of a trapezoid. So this is something you're going to want to make sure you know for your AP exam. Okay. Or f of x 0 plus f of x1 over 2 times delta x. So for trapezoid number, this is what you'll get. Okay. So delta x, if you're doing one subinterval, is just x1 minus x0. So we're going to go through and do all of these. So trapezoid number 1, f of x0 is f of 0 plus f of 3 over 2. And your delta x is 3 minus 0. So this is going to give us 4 plus 10 over 2 times 3. That gives us 21. Okay. Trapezoid number 2 is going to be f of 3 plus f of 5 over 2 times 5 minus 3, which is going to give us 10 plus 8 over 2 times 2, which gives us 18. Trapezoid number 3 is going to be 5, 9, 2. Okay. Let's fix this. Okay. Times 9 minus 5. So this is going to give us 5 is 8 plus 5 over 2 times 4. The trapezoid number 3 gives us 26. And last one, trapezoid number 4 is going to be f of 9 plus f of 12 over 2 times 12 minus 9. F of 9 is 5, f of 12 is 11, 12 is 3 is going to give us 24. So our total area is going to be 21 plus 18 plus 26 plus 24, which is 89 square units. So the difference here is we are not getting our y values or our different side lengths of our trapezoids or heights, if you want to think of it that way, from a graph. You're getting them from a table. So they're still y values, and you're matching them up to matching x values. It's just you're doing each trapezoid one by one. So your one trapezoid is coming from here to here. And your next one is going from here to here. So if you were to graph it, that's essentially where those trapezoids are coming from. Okay, so if you don't have a standard delta x, you can't do the shortcut. So what I would know if I were you is I would make sure you know the area of a trapezoid, and I would also make sure that you know the sort of shortcut method up here. Okay? And that is 5.2.